Okay, so here's Unit 1B, Lesson A, Vectors and Vector Resolution. For this unit, we're going to continue to develop our ability to describe the motion of objects, but now we're going to look at two-dimensional motion, which means we're going to be launching objects so they travel through the air in what's called a trajectory. In our exploration of two-dimensional motion, we're going to ignore air resistance. We're going to assume all objects are point masses, which means their mass is concentrated into a single point. And that's just going to be standard throughout the unit as we look at projectile motion. But to begin, we're going to build some skills in vector addition and vector resolution. So what we've done so far is this one-dimensional motion where we have constant velocity and we used our kinematics equations. Those all required skills with being able to do free fall, motion graphs, PT, VT, and AT. Okay, so now in two-dimensional motion, we're still going to be using the same kinematics equations, but we have to add the skills of vector addition and vector resolution to this. Our learning targets for vector analysis is we want to be able to resolve vector velocity and displacement vectors into their components. We want to be able to calculate the magnitude and direction of velocity and displacement vectors given their components, and determine the net displacement of an object when given more than two initial displacements. So, scalars and vectors. A scalar, as you remember, is a physical quantity that has a size but no direction. It's got magnitude but no direction. So we can say speed is a scalar. Okay, you can go 20 miles an hour, right? It becomes a vector when that physical quantity has a direction, 20 miles an hour to the east. So, we talk about scalars and vectors. Vector resolution, we're dealing with quantities that are vectors, displacements, velocities, accelerations, those kinds of things. And in further units, we're going to add other vectors to what we're studying. So we can also talk about what's called a resultant vector. A resultant vector is a vector that represents the sum of two or more vectors. For example, say you're walking from home and you walk to school and then you walk to the library over here. You're taking your displacement from home to your eventual location, the library, is your resultant vector. Okay, so we draw these vectors using what we call vector arrows. Okay, the vector arrows are always drawn so that the tail of the vector is on the object and the arrow points in the direction that that vector points. And it's important that it's an arrow so you understand, so somebody looking at it understands that it is a directional, that's the direction that that vector is pointing. Then we're going to label that vector with what it is, whether it's a displacement or a velocity or an acceleration. Now, all vectors have a set of properties that are common to all vectors. Okay. First, vectors can be moved parallel to themselves in a diagram. So here we've got Link here, and he's about to run across this conveyor belt. Okay. So Link has a velocity vector in this direction. Okay. Because Link is the object, we put the tail of his velocity on him. Okay. Now, as Link, as you know, if you played a game like this, you know that as Link goes across this conveyor belt, he's going to also be moved to the right because the conveyor belt is moving. Now, when we go to put the velocity vector for the conveyor belt here, we're going to put it on Link because that velocity is affecting Link. Okay, so this would be a correctly placed vector diagram for the object. Right down here, this is the object. It's Link. These vectors are acting on Link. Okay. What this property means, vectors can be moved parallel to themselves in a diagram, is it does not change either of these vectors. It doesn't change them at all if I just move one from there over there. So if I can move the arrow representing link's velocity vector to the tip of the velocity vector of the conveyor belt, and it doesn't change that vector at all. Okay, I could also move this one up here, right? And it's very important, it's important and quite obvious that when you do that, we end up with this right triangle right here. Okay, so this arrow that I just drew on here represents the resultant velocity vector. It's going, when Link goes across the conveyor belt, it's going to be as though he is running with a velocity of this size, of this magnitude, in this direction. Okay, so of this in this direction. Now, if we want to know, if we are told Link is running with a certain velocity, say he's running at 3 meters per second, and the conveyor belt over here is going at 4 meters per second, it's pretty obvious what this resultant velocity is going to be, right? And we'd be able to figure it out easily by using Pythagorean theorem. A second property of all vectors is that vectors can be added in any order. So you say you're a marathon runner, and you run a marathon, and you start at this point, and it ends at this point over here. Okay, it doesn't matter if you run this pathway or if you run this pathway. The displacement is the same. Okay, so we can add up those vectors in any order. Also, if we want to subtract a vector, we simply add its opposite, or we'll often talk about a negative vector. It just means that when we talk about a negative vector, like if we have a displacement and we say that somebody's displacement is a negative 5 meters, right? That just simply means that it's a displacement in the negative direction. It's not like they displaced less than 0, okay? And then also, finally, multiplying or dividing vectors by scalars results in vectors. It's not possible to add scalars and vectors. Okay, so in order to determine the resultant magnitude and direction here, we're going to go back to Link. So again, Link running this way, conveyor belt runs this way. I can move either of those velocity vectors to the tip of the other, and it doesn't change the character of that vector at all. Okay, but what that does is gives me my resultant vector over here, and obviously now I have a right triangle. So in order to figure out what this resultant velocity is, if we want to know also the angle, then right here, we're often going to want to know what that angle is. We're going to use the Pythagorean theorem right here to figure out the size of that vector. And then we would use a tangent function to figure out what that angle is, the opposite over the adjacent. Okay. So let's take a look at an example. We have an archaeologist climbs the Great Pyramid in Giza, Egypt. The pyramid's height is 136 meters, and its width is 230 meters. So we want to know the magnitude and direction of the displacement of the archaeologist after she's climbed from the bottom to the top of that pyramid. So as she walks this pyramid, obviously she's going to go this direction, but that's the same as moving 115 meters this way and then climbing a ladder 136 meters up. You would get the same thing. So what we have here are two displacement vectors that result in this displacement vector here. Okay? We call these two vectors the components of this resultant vector. Okay? So in order to figure out the total displacement, okay, from the bottom to the top, we can simply use a Pythagorean theorem. Now, when we do this, we could write a squared plus b squared equals c squared, and that's kind of the math way of doing that. In physics, we want to be specific about the vectors we're talking about. The diagram has labeled them delta x and delta y and d, so we're going to preserve that in our calculation. We'll substitute in our known values, calculate and come up with our answer. So now we want to look at resolving vectors into their components. That was getting a result. What we just did in that example was getting a resultant vector from the components. Now we want to look at resolving the vectors into components. So the components of a vector are the projections of a vector along the axes of a coordinate system. So for example, if we have a displacement and we represent that displacement here, right? Here's our displacement. That displacement has two component vectors. It's got one in the x direction, so we would call that, say, dx, and it's got one in the y direction. We call that dy. Okay? So those are the components of that vector. Let's take a look here at this plane and truck. Okay? So the plane is flying off at an angle. Okay? The plane has component vectors, one in this direction and one in this direction. You can't really see that. So the plane has an x and y component. The truck also has an x and y component to its velocity vector. It just happens to be that that y component is 0, right? So it only has the x component of the vector. So say this truck is carrying this film crew. It has to be driven at the right velocity to enable the film crew to stay directly underneath the plane. The plane flies at 95 kilometers an hour at an angle of 20 degrees relative to the ground. Does this truck have to be going the same overall speed as the plane, or is it something different? If the plane is flying off with this velocity, and it has a velocity vector in the x direction, it has a vx, it also has a vy, right? So that plane, its velocity is split kind of into two different directions, into that horizontal direction and that vertical direction. So the truck down beneath here has got to travel at a velocity only equal to the x component of the plane. Okay? So in order for that truck to stay beneath the plane, the truck has to be driven with a velocity equal to the x component of the biplane's velocity, okay? Which is not, it's something less than 95 kilometers an hour. So to figure out what that is, that's where our sine and cosine can come into play here. If we want to know what Vx is, Vx, right, is the adjacent side to this angle right here, okay? So that's right here. So if we use the cosine of 20, if we go cosine 20 is equal to the adjacent side, which is Vx, remember preserving what our things are labeled, and the hypotenuse is labeled as V plane, okay? Well, Vx is what we're looking for. V plane is this 95 kilometers an hour. Cosine 20 times 95 gives us 89.3 kilometers an hour. That's how fast the truck would have to actually go to stay directly beneath the airplane. So let's take a look at an example then of resolving vectors into their components. We have here a helicopter traveling at 95 kilometers an hour at an angle of 35 degrees to the ground. Okay, so this is our resultant velocity, right? This velocity has components Vx and Vy. We want to know what those components are. So Vx is going to be equal to the resultant velocity times the cosine of the angle. Okay, take a minute and pause to make sure you realize where I get that from cosine is adjacent over hypotenuse. Okay, so substituting values and doing our calculation, we see that we get Vx is 77.8 kilometers an hour. If we want to know Vy, okay, now remember, because we can move a vector over, right? We could actually draw this velocity vector, this Vy, over here, just like this, right? Making this Vy opposite our angle here, okay, which would give us our sine function. So for Vy, we're going to go V sine theta and substitute in our values. And our Vy ends up 54.5 kilometers an hour. Okay? So this helicopter going up at 95 kilometers an hour at an angle of 35 degrees is exactly the same as traveling at 77 kilometers an hour directly along the ground and straight up at 54.5 kilometers an hour all at the same time. Now we often will be in situations where we're going to be adding vectors that are not perpendicular to each other. So we're going to take a minute and look at that situation. So let's say we start with two displacements. They're right here. These two displacements are not at right angles to each other. You have a displacement that somebody walks at this angle, turns and walks at this angle, this distance. Okay, and we want to know what our resultant displacement is. What is the displacement from this point to this point? Okay. Well, both these vectors are at angles, so both those vectors can be resolved into their components. Okay. We can take D1 right here, and we can resolve D1 into X1 and Y1. Okay, those are the components of that displacement. Then we have displacement D2. We can also resolve that displacement into its components, X2 and delta Y2. Okay? When we do that, then, because the vectors can be moved parallel to each other, they can be moved parallel to one another, we are able to slide those around so that all of the X components are in line with one another and all the Y components are in line with one another. You can see from these two diagrams that it's really the same thing. We've just taken X1, kept it right there. We take X2, delta X2, and bring it down even with delta X1. And delta Y1 and delta Y2 are moved over here so that they are at the tail of delta Y1 and delta Y2 are at the tip of our X components, giving us our right triangle here from which we can find our resultant displacement. Okay, so this is what we end up with from this original diagram here. Okay, so if we find delta X1 and find delta X2, we can add those two together. We can add delta Y1 and delta Y2 together, and then we have the components of our displacement vector. So let's look at an example of how to do this. Say we have a hiker walks 27 kilometers from base camp at 35 degrees south of east. Next day she walks 41 kilometers in a direction 65 degrees north of east and discovers a forest ranger's tower. We want to find the magnitude and direction of her resultant displacement between the base camp and the tower. So let's start by kind of analyzing the diagram right here. Okay. In this diagram, each of these displacement vectors have their own components. Okay, so D1 has got a component in the x direction and a component in the y direction. D2 has a component in the x direction and a component in the y direction. Okay, so we're going to call D1 x. We're going to call the x component of D1 D1x. We're going to call the y component of D1 D1y. We're going to call the x component of D2, of course, D2x, and then we'd have D2y. Okay? So to go apply our trig functions here, we have to look at each of those components. Look at D1x right in here. Okay? D1x, right here, it's adjacent to theta 1, so it's adjacent to that 35-degree angle. So our expression then for D1x is going to be D1 cosine theta 1. Okay? Our expression for D1y is opposite that theta 1, that 35-degree angle, because we can slide that D1 y over to be opposite it. So D1y is going to be D1 sine theta 1. Okay? So when we go and substitute in our values, we've got 27 kilometers, we've got an angle of 35 degrees, so our D1x ends up 22.1 kilometers. Okay? D1y then, we're going to throw in here 27, that's D1, sine of 35 is 15.5, but something very important to look at with D1y. D1y is pointing down. It's pointing in the negative direction, and so when we recognize that, we see that, we make sure that we report it as a negative displacement, 15.5 kilometers. Okay? We'll do the same expressions for D2x and D2y, substitute in their values, and here's what we end up with. 17.3 kilometers for D2x, D2y is 37.2 kilometers. Now, let's take a look then at what we have here, and we're going to draw this out. So we've got D1x, here at 22.1 kilometers. We've got also in the x direction, we have D2x at 17.3 kilometers. So we draw it slightly shorter. We've got 17.3 kilometers. In our y direction then, we have a D1 of negative 15.5, okay, and D2y of 37.2, a positive 37.2. So what we look at as these y components, one goes down, one goes up, we can subtract the, can take out the negative out of the positive, okay? So when we go to do that, we're just going to take this 37.2, subtract the 15.5 from it, right? And we really end up with a y component of 21.7 kilometers, okay? And we can add the 22.1 and the 17.3, and we end up with a 39.4. So what we really have here is a displacement where we have an x component at 39.4 kilometers and a y displacement of 21.7 kilometers, and all we have to do with this is find then our resultant. It's just like what we've done previously here. So applying that Pythagorean theorem, we end up with the resultant vector drx, the resultant component in the x direction squared, plus the resultant component in the y direction squared, gives us the square of the resultant vector. If we substitute in our values and do our calculations, here's what we end up with. We end up with a resultant displacement of 45 kilometers at an angle of 28.8 degrees. Finding this angle, right here we use the tangent function. It's the opposite over adjacent, so it would be dry over drx. The 21.7 divided by 39.4 gives us 0.55. Then you have to apply the inverse tangent in your calculator to get this 28.8. And that's kind of a really important note here. As we do work with vectors and we do these trig functions, it's going to be very important that your calculator is always set in degree mode, not in radian mode. Okay? So that's it for Lesson A, Vectors. See you in class.